Good morning, everybody. Hope you're all healthy and safe at home. Let us continue with our section 9.9, Independence of Path. So in the previous class, we had just introduced the concept of path independence, and we had seen that if the vector field is conservative, then we can assure that the line integral over C is any curve, f dot dr, it does not depend on the path of integration, but only on the initial and the terminal points. So in this lecture, we are going to discuss about the theorem, which is called the fundamental theorem of line integrals, which assures us that the line integral is independent of the path if the vector field is conservative. So the statement of the theorem is as follows. Suppose C is a path in the open region R of the xy plane and is defined by R of t is equal to x of ti plus y of tj, where t varies between a to b, a less than equal to t less than equal to b. And if f of x comma y is equal to p of x comma yi plus q of x comma yj is a conservative field in R and phi is the potential function for f, then we have integral over C f dot dr is equal to integral over C grade phi dot dr, which is further equal to phi of b minus phi of a, where a is equal to x of a comma y of a and b is equal to x of b comma y of b. So I hope the statement is clear. Just go through the statement of the theorem once again. Just keep in mind what all we have and what we have to find. So let's move on to the proof of this theorem. We are given f of x comma y is equal to p of xyi plus q of xyj. The curve is defined by, that is C is defined by R of t is equal to x of ti plus y of tj. Now, if R of t is x of ti plus y of tj, what will be R dash of t? This will be x dash of t I plus y dash of t j. So this can also be written as dx by dt I plus dy by dt j, right? So r dash of t is dx by dt I plus dy by dt j. Now just recall one thing. If we are given a function, vector function r of t, then dr can be written as dr by dt into dt, right? Now what is dr by dt? This is nothing but r dash of t. So we get, if we are given a vector function r of t, then dr is equal to r dash of t into dt, right? Now let us find the integral part. Integral over C f dot dr can be replaced by integral over C f dot, instead of dr what can we have? We can have r dash of t into dt. Okay, this much is clear. Now, given f is conservative, right? Given f is conservative vector field. So, we can find, and the potential function for f is also given, and let's just mention it. Phi is the potential function. So by definition, what do we get? We have f is equal to grade of phi, right? So let us replace this value also in our line integral. So what do we get? Integral over c f dot dr is nothing but integral over c f is grade phi dot r dash of t into dt. Now let us find what this term is. What is grade of phi? Grade of phi is dou phi by dou xi plus dou phi by dou yj. And we had seen in the beginning of this proof that r dash of t is dx by dti plus dy by dtg. So what will be the dot product of grade phi and r dash of t? It will be nothing other than dou phi by dou x into dx by dt plus dou phi by dou y into dy by dt. So this is grade phi dot r dash of t, right? Now what was our integral? Integral over c f dot dr was integral over c grade phi dot r dash of t into dt. Now just look at this term. If phi is some function of x and y, okay, and this x and y are further function of t, then we can calculate dou phi or d phi by dt will be the partial derivative of phi with respect to x into dx by dt. Here we are applying the well-known chain rule which we have discussed many times in previous sections into dy by dt, right? So this was the term which we had in our line integral. So this is integral over c f dot dr will be nothing but integral over c. Instead of f dot dr, we first replaced it by grade f dot r dash of t into dt, and grade f dot r dash of t was nothing other than d phi by dt into dt, and this is nothing but phi of x comma a y comma x comma b y comma b minus phi of x comma x of a comma y of a. So that is, it was considered in the theorem that this is b and this is a, right? Integral of differential will be the function itself, that is phi, and the variation of t is from a to b. So we got that integral over c f dot dr is nothing but phi of b minus phi of a. So I hope the proof is clear for all of you. We had seen that the theorem which states or which assures that the conservative field, if we are considering the conservative vector field, then the integral over c, the line integral, it does not depend on the path but only on the initial and the terminal points. So it is a very much simple proof. We just have to remember what are the replacements that we are giving. So now let us do one thing. We shall see or visit the example one which we had done before. That is, we had to evaluate integral over c y dx plus x dy, where c is a path from 0, 0 to 1, 1. So you can see in figure 9.9.2, we have 2 points, that is 0, 0 and 1, 1, that is the initial point and the terminal point, and we are just considering any curve, say C. Okay. Now this is the curve, the figure of the curve. Now we had seen that if we consider the function phi of x comma y is equal to xy, then f can be replaced by grade of phi. That is, f was a conservative field. We had discussed this in the previous section. So from this theorem, if we have to calculate this integral using the above theorem, fundamental theorem, what can we do? We know that f is equal to grade phi. So we just have to, the evaluation will be simple. We just have to calculate phi of b and phi of a. Right? Here the terminal point is 1, 1. So what will be phi of 1, 1? That is nothing but 1 itself. And what is phi of 0, 0? That is 0. So by fundamental theorem, the value will be phi of 1, 1 minus phi of 0, 0. That is 1 minus 0, which is equal to 1. So if we are dealing with conservative vector fields, we can calculate the integral, line integrals using the fundamental theorem in a very simple manner by just knowing the initial and the terminal points. Now, as we had, we all must be familiar with the fundamental theorem in calculus. That is, integral of f dash of x into dx is nothing but f of x itself. So in that case, we can use any antiderivative of f dash of x, that is f of x plus k. If we consider the function f of x plus k, where k is any constant, then what will be the derivative of f of x plus k? It will be f dash of x plus derivative of constant is 0. That is, we get f dash of x itself. So if we use any function f of x plus k, the derivative of this will be f dash of x itself. So in a similar manner, here we are using the potential function phi. So here also we can consider phi of x comma y is equal to xy plus any constant k. The integral value will remain the same. Why? Because we know that by the theorem that integral a to b f dot dr is phi of b minus phi of k. So what will be phi of b? We have to substitute the value of x and y here, terminal point. But k will have no substitution, right? So phi of 1, 1 is again 1 plus k. And phi of 0, 0, referring to the previous example, phi of 1, 1 is 1 plus k, and phi of 0, 0 is 0 plus k. So when we subtract them both, k and k will again get cancelled. So you get the same answer. So we can use any function phi of xy plus k, where k is any constant value. So that is how we had discussed about the fundamental theorem, which is important in calculating the integral, line integral of a curve. So next we are moving on to some definitions regarding the region, which we are going to discuss in the next few sections and all. So first of all, a region in a plane is said to be connected if every 2 points A and B in that region can be joined by a piecewise smooth curve which is entirely in the region itself. Okay. A region is said to be connected if we can join every point in that region by piecewise smooth curve which lies in that region itself. And a region is said to be simply connected if it is connected and every simple closed curve lying in the region can be shrunk or contracted to a point without leaving R. So this is a bit difficult to understand, but the main concept is that a region is said to be simply connected if it has no holes in it. Okay, if we have any hole in it, then if one point, if we have holes in it, then we cannot construct, we cannot shrunk or we cannot expand that particular curve without leaving the region, because there is possibility that we will move to that hole and the region will not be, that curve will not lie in that region. So when we go into when we see the figures which are given in your textbook, we will get a more clearer picture. Next is a graph is a region is said to be disconnected. We know when it is connected. If it is connected, when 2 points can be joined by piecewise smooth arc or curve, and it is said to be disconnected if it is not connected. Okay, and the next definition is about multiply connected. That is a region which is connected but not simply connected. Okay, that is any 2 points can be joined by some curve which lies inside that region itself in some way or the other, but it is not necessary that that region will not have any holes in it. There can be holes in it, and we can form any curve suitably also. And the last definition is, it is simple by the name itself. A region is said to be open if it contains no boundary points. Okay, like the xy plane and all. It is unbounded. You can just expand it to whatever point you want to. So let us just see the figures which are given in your textbooks. So you can see figure 9.3. You can see first A gives the connected region. That is, if you are considering any 2 points A and B, you can draw curve, piecewise smooth curve, in such a manner that it lies inside itself. So if you take any points here and here also, you can join it by a line. You can join it by any curve without moving out of the region. That is, if you take one point here and another here, we can join it like this, right? So there is no necessity for us to get outside this region. And 9.9.3b gives us a region which is not connected. Clearly, if we take a point in this region and the other region, we cannot join them by a curve which lies in that region itself. It is outside that region. And finally, the multiply connected region. See, can you see that there are many holes in it? This is the region which you are considering, but there are holes in it. Okay, but still, if you take any 2 points, if you take one point here and the other point on this side of this hole, we can join it by a curve. But we cannot reduce the size or expand the size without going outside this region. Because if we try to reduce the size, there is a possibility that we'll enter into this hole. So if there are no holes, the region is said to be simply connected, and if there are holes in it, the region is said to be multiply connected. So these are the few definitions that we must keep in mind before moving on to the further discussion. So with this, we'll wind up our class. Thank you. Stay home and stay safe.